Okay, so we just learned how to take non-abelian covariant derivatives, and we saw this required us to introduce a non-abelian gauge field, a mu of A. Now that we have this, of course, we should try to build a gauge invariant action involving it, and that's what we're going to do now. We're going to, again, do this in pretty much the same way as in the usual abelian case. In particular, let's consider, just like we did there, the commutator of two covariant derivatives acting on our field psi. So I'm going to look at d commutator d nu acting on the field psi. Okay. So what do we have? Well, if we consider a gauge transformation of this, we know that by construction d nu psi transforms the factor of u, and so does d nu psi. And so we just get an overall factor out front of u of x times the commutator of d nu of psi. And now, again, just as before, it turns out that this thing is just equal to a linear operator acting on psi with no derivatives. Let's call that linear operator f mu nu A. Sorry, I left out some factors. Let's call that linear operator minus ig f mu nu A ta acting on psi. In particular, there are no derivative terms here. So this object here, f mu nu A, has a nice gauge transformation properties and is a natural thing for us to think about. Just like before, we're going to call this the field strength tensor, where again the difference is now that it also has a non-abelian gauge index A. Okay. So let's work out explicitly what this guy is, what this f mu nu A is. To do that, I'll just expand this out using the definition of the covariant derivative. So in particular, I'm going to expand out this object here. Okay, so what is this? Well, if I work it out, then you can see that there are a couple of terms where this whole thing is acting on psi, sorry. Now if you expand this out, you can see that there are a couple of terms where the derivatives act on the gauge field. So for example, when this derivative acts on this gauge field, you get a term that looks like A nu A minus D nu A mu A. Okay. And again, this is the opposite combination of derivatives and gauge fields. And then there's also a term which comes from the gauge field squared, which looks like g squared A mu B. Oops. A mu A nu B. And then there's the commutator of the representation matrices acting on psi. And of course, this piece here is the new bit coming from the non-abelianness of this. This would not have been there in the abelian case. Now if I continue to work this out, then I can use the definition of the structure constants to further write this in the following way. A mu B, A mu C, F B C A. TA, all acting on psi. So now if I compare this object to my definition right up here, I see that the components of the field strength are that f mu nu A is just d mu A nu A minus d mu A nu A plus g A mu B A nu C FABC. Okay, so these are the components of the non-abelian field strength tensor. So again, there's a piece of this which should look familiar from the abelian case. Then there's some extra non-abelian bit that comes in here that has to do with the non-trivial commutator structure of the representation matrices. Now, importantly, from our previous study, in other words, from doing somewhat more abstract considerations of how things like this transform, we know that under a gauge transform, the way in which f mu nu transforms is that f mu nu, which is f mu nu, f mu nu prime, which is notation for f mu nu a summed over the TA, transforms in the following way. It's equal to the unprimed guy conjugated with a u and a u dagger on either side. Okay? In other words, f mu nu transforms in the adjoint. Okay? And again, this follows from thinking about the definition of f mu nu in terms of the commutator of two covariant derivatives. Okay? And you might sometimes be interested in the infinitesimal version of this transformation. Just like in the gauge field case, you can work out what that is. And the infinitesimal version of this transformation is the following: f a b c alpha b f mu nu c plus order alpha squared. Okay. So this is infinitesimal, where again you can think about u as being the exponential of I alpha TA. So this we have sort of argued a bit abstractly from the thinking about the commutator. You can also prove this explicitly, and the way we should do that is take all of the guys appearing here and explicitly gauge transform each of these A's, and you will see that this transformation comes out. Okay, and this transformation comes out. You might remember that this involves, in fact, a very particular combination of terms, canceling, and so the precise factors of G and so on that appear here are actually extremely important. And finally, those of you who've taken GR, all of you I suppose, might recall that this construction is pretty much how we construct the Riemann tensor in general relativity. The Riemann tensor is very closely analogous to this field strength tensor, and the considerations about commutators of covariant derivatives and all are really directly, they can be directly related. Okay, so now that we have this object, we can construct a non-abelian gauge invariant action for this gauge field. Okay. And this is basically completely unique. Let me just tell you what it is, then we can discuss its properties. Just take the trace of the matrix valued field strength squared. Okay. So this is the definition of basically the only possible action for this gauge field. Okay. So this is called the Yang-Mills action for non-abelian gauge theory. Okay. Where I remind you that f with no superscript is just the sum over f mu nu a times TA. Okay, that's it. That is the Yang-Mills action for non-abelian gauge theory. Let's check some of its properties. So first of all, let's make sure that it's gauge invariant. Under a gauge transformation, what happens? Well, we have trace of f mu nu prime, f prime mu nu. From this transformation law above, we see that the way that f transforms is by conjugation with u and u dagger. So this goes to trace, put this on the second line, trace of u of x, f mu nu, u dagger of x, u of x, f mu nu, f mu nu, u dagger of x, And then these cancel. We take the trace. This one comes around and cancels against that. And so we find that this is equal to the trace of f mu nu. F mu nu. So indeed, it is gauge invariant. Okay. It's also a component to work this out in components explicitly. So let's do that. So what is the trace of f mu nu? F mu nu. So if I work this out in components, then this is this. Now, of course, this trace is a matrix trace, and so it only acts on the t's. And so what we have then is that this is equal to minus a half f mu nu a, f b mu nu, times trace of ta tb. Now, from your group theory course, you might recall that it's always possible to pick the generators of SUN. So you can pick the TA so that the following is true. The trace of TA TB equals to 1/2 delta AB. And if you do that, or rather if you pick your TA so this is true, this is a convention that we will use always, we will assume this is the case, then what you find is that the Yang-Mills action is just the integral d4x minus 1/4 f mu nu a, f mu nu, f a mu nu. Where again there's an implicit sum over all of the Lie algebra indices of the gauge field A. Okay, that's it. This is what S Yang-Mills looks like in components. However, I want to point out that actually this action looks really simple. It's actually kind of complicated because you see, unlike in the abelian case, F is non-linear in the gauge field. So even though I've written the action in a very compact manner, it's actually already a non-trivial interacting field theory. It's not quadratic. Okay? And so we're going to study the quantum aspects of this theory in the next video. For now, let's study a few classical aspects of this. Okay. So let me first figure out the classical equations of motion by varying this action. Okay, so I'm going to go through this a little bit explicitly. So first, let me just consider the variation of delta S Yang-Mills. So what is that? Well, that variation is the integral over all space-time times minus a half f a mu nu times delta f a mu nu. Okay. Or I've just varied this. I've just taken the variation of this, factor of 2, because f is squared. Now, let me write out explicitly what this is. Let me try to do this correctly with no typos. This is the integral d4x f a mu nu. And now here I'm going to plug in the definition of f in terms of the abelian gauge field, non-abelian gauge field, sorry. So there's a term coming from the antisymmetric derivative of a. And there's also a term coming from the part that is like a squared. And that part looks like this. A nu c plus a mu b delta a nu c. And the whole thing is multiplied by FABC. And so now, if I take this and I combine some terms together, then I can write this as the integral d4x. So I now integrate by parts on these derivatives, and that has them acting on this guy instead. Because there's two of them, I get another factor of 2 with a minus sign. So I get a term like this. And then relabeling indices on the second term, I get a term that looks like this, FABC A mu b, and you can check that the other terms assemble together to simply make this into fc mu nu. And the whole thing is multiplied by this variation. Sorry, delta A. Yes, now it works. Okay. And from here, we need to demand that this vanish. So what that implies is that the equations of motion are delta mu fa mu nu plus g fa bc a mu b fc mu nu equals to 0. Okay. Those are the equations of motion. Now, if you look at this, this is actually extremely elegant. Let me tell you why. Notice that what you're trying to do here is take the derivative of something that transforms in the adjoint. Okay, so we're taking the derivative of f mu nu a, but f mu nu a transforms in the adjoint. We already know that because f transforms as u f u dagger. That's the definition of something transforming in the adjoint. And you know that you can't quite take the derivative of something that transforms in the adjoint under gauge transformations. You have to take the gauge covariant derivative of it instead. And in fact, that's exactly what this term does. This term makes it so that you are computing the gauge covariant derivative of f mu nu a. Oops. So that is, in fact, exactly what this equation is. It is the gauge invariant divergence. So the gauge covariant divergence of f. And if you think about it, this is the natural generalization of the abelian equation of motion, which was just d mu f mu nu equals 0. Here it's the gauge covariant divergence of f. Okay. So this is the so-called classical Yang-Mills equation. Again, the notation is very elegant and makes it look very simple. It's really quite a complicated nonlinear equation because f contains nonlinear terms in it. Now finally, we can also couple matter to these gauge fields. Let's discuss how to do that. So this was all discussing the dynamics of the pure gauge field alone. We can also couple matter to them. So there's really a very sort of systematic algorithmic way to do this. Let's discuss the rules. So the rules are to construct a non-abelian gauge theory. So rules to make a gauge theory. Step 1, pick a gauge group. Let's call it G. Step 2, pick some matter content. For example, you might have some fermions, psi, so on. And step 3, pick a representation for the matter to transform in under G. And then just write down the action. So what is the action? Well, for example, if I have one set of fermions, then the action would be the integral of d4x. There is a kinetic term for the non-abelian gauge field, trace of f squared. Sorry, try to write this a bit more nicely, given its importance. And then there's a term like psi bar I d slash minus m times psi. where here this d slash now is the non-abelian gauge covariant derivative, and it is d mu psi, which is partial mu psi minus ig a mu a ta psi. And here you pick the ta, so pick the ta matrices depending on which representation psi is in. And that's it. You're done. Again, this is the most general renormalizable action. Okay. And again, it depends only on a single parameter g. And that parameter g, the gauge coupling, is actually hidden in the gauge covariant derivatives, so but it is there. And I guess I shouldn't say it depends on the single parameter. Of course, the mass of the fermion also matters. But the interaction structure of it is completely controlled by this single parameter g, the gauge coupling. Okay. So given this, you can now work out the classical equations of motion of this theory. And let me not go through details, but the classical equations of motion of this are, from varying the action, you get the bit from the kinetic term, which is just this, and this turns out to be equal to minus g times psi bar gamma nu Ta times psi. Okay, that's the gauge field equation of motion, and the Fermion equation of motion is it's just this. So notice that there's a new term on the right-hand side of the gauge field equation of motion. That's coming from the interaction of the fermion with the gauge field through this term. In fact, if you stare at this, you can see that this can be understood as the Noether current that you would have had for psi if you treated the gauge symmetry as a global symmetry. Okay? So in particular, in a few lectures ago, I discussed how to construct the Noether current for a global symmetry. If you pretended this gauge symmetry was a global one and constructed the Noether current, you would get exactly this thing here, which appears on the right-hand side of the gauge equations of motion. And that's a general principle. The source for the gauge equation of motion is always related to the Noether current of the symmetry that the fields transform under. Okay, so now let me say a few words about this classical action. So first of all, notice that it looks like we have n square minus 1 types of massless gauge field, right? Because you can see that we pretty much have a bunch of fields A. There's no mass terms for A. So it looks like we have some A mu A. So here A runs over 1 blah, blah, up to the dimension of the gauge group. So if we had SUN, it runs from 1 up to n squared minus 1. So what that means is it looks like we have n squared minus 1 massless gauge fields. In the non-abelian context, massless gauge fields, or gauge fields, are usually called gluons. Okay? Looks like we have n squared minus 1 massless gluons. One of them for each Lie algebra element in the theory. And next, I also want to point out that the action here, this action here, is exactly the action for QCD, quantum chromodynamics, the theory of the strong interactions. So it's almost exactly the action for QCD. So let me write down the proper action for QCD. In QCD, in quantum chromodynamics, we have n equals to 3, so we're looking at a SU3 gauge theory. And we have a bunch of fermions, okay? The fermions are called quarks. And each of the fermions, each of the quarks, transforms in the fundamental under SU3. So in fact, I shouldn't have called them psi. We typically call them Q for quark, but these are all fermions. How many different kinds of quarks do we have? Well, here this index I runs over all the different types of quarks, and those types of quarks that you might have heard are called up, down, top, bottom, charm, and strange. And indeed, they have very whimsical names. Okay. And they all have different masses that you can look up. And the full action then for QCD takes the following form. As QCD is a function of Q bar, Q in the non-abelian gauge field. It's integral d4x minus 1/2 trace of f squared plus the sum over all the different kinds of quarks, Qi. id slash minus m Qi. And each of the quarks has a different mass, and you can look up what those masses are. They're pretty much very heavy except for the up and down ones, sorry. The up and down ones are the everyday kinds of quarks. Okay, and that's it. This is the action of the famous theory of the strong interactions, QCD. All right, so now that we have this, this theory, let's just briefly discuss some physical implications of it. So let's look at some simple solutions to the Yang-Mills equation. By which I mean to the classical Yang-Mills equation. So the quarks are in the fundamental, and what that means is they come in 3 varieties. Okay, there are 3 components to each quark because it transforms in the fundamental under SU3, and those 3 types. So the fact that each of the quark flavors, each of the quarks, I'm not being very careful with the notation here. Each of the quarks is a 3-component object, and these 3 components are called color for some reason. So let's pick a direction in this SU3 space. And call that direction red, because it's one of the 3 colors. Now, let's imagine that we can classically get one of the quarks to sit at some point x. Okay? So I have a quark and it's just sitting there at some point x. In that case, you can convince yourself that if you stare at this right-hand side of this Yang-Mills equation, then this current here is going to be a delta function localized at that point x. And if you work out carefully what the Yang-Mills equation is there, then you can see that you get, for the time component of the Yang-Mills equation, you're going to get something that looks like this. The red component of the representation matrix multiplying a delta function in position space. Okay, where again red is just one of the directions in the SU3 space. The others are, as you can imagine, called green and blue. Okay, this is just a particular component. If you're upset about the red, you can just think of it as the 1,1 component of one of the representation matrices in the fundamental rep. And this is the sort of vision you get to lowest order in G. Okay, the lowest order in the coupling. Now, there are all kinds of different terms in here, proportional to like nonlinear things like G, FAB, A squared. You can show, in fact, that they don't actually contribute. So if you dissect this equation, it turns out you get a Maxwell type equation that looks like this. G times some number times a delta function in space. Okay. And this is a Maxwell type equation. And in fact, this should have an inverse square solution. You can solve this, and you can show that there's something that looks like FART goes like 1 over r squared. So in other words, if you have a quark sitting at this point x, and you look at what's happening at some distance r away from that point x, there should be a TR component of the non-abelian field strength, which goes like 1 over r squared. What we say is it has a color electric field that goes like 1 over r squared. Okay? So in other words, this theory is making a prediction. It's saying that if you have a quark, then that quark should make a color electric field that goes off like 1 over r squared. Now, is this correct? So if you think about it, this is completely wrong physically. If you look around the room, you don't even see ever an isolated quark. In fact, the gluons aren't massless in real life. You can't see any massless gluon fields floating around. You can't ever see a single isolated quark, let alone verify that the quark makes a color electric field that goes off like 1 over r squared. Okay? So what's happening here? Why have I told you this theory, which seems so terribly wrong? And what's happening here is really the following. There's a big difference between the abelian gauge theory and the non-abelian gauge theory. Okay? And the difference is, in the abelian gauge theory, in Maxwell E&M, the classical theory, okay, the classical equations of motion of the abelian gauge theory are a good representation of the real quantum physics. So you can more or less get the right answers in E&M just from looking at the classical theory alone. So in the abelian case, classical physics is not that different from the quantum physics. Okay? And that's why the equations of motion that you get from varying the Maxwell Lagrangian, you study those in elementary physics classes. However, in the non-abelian case, this is not true. In the non-abelian case, the classical theory is a terrible approximation to the quantum theory. And so what that really means is we really have to study the quantum theory to understand the physics properly. And that's why in the next lecture, we're going to finally quantize the non-abelian gauge theory. And we'll try to make sense of these physically completely wrong predictions of the theory that we've written down so far. Okay, see you in the next video.